This episode is brought to you by Brilliant. As we move into the future and expand off planets, we tend to design our megastructures and habitats to our own bipedal, land-based desires. But what about our oceanic friends, like super smart dolphins, or if we find marine life in the ocean moons of Jupiter, or if we decide to re-engineer ourselves into more men and more maids? So one of our most talked about topics on this channel is the general concept that humanity is likely to build giant space habitats as opposed to simply terraforming and colonizing other planets. And today we will be discussing that notion in the context of building oceanic and aquatic habitats in space. We will introduce some new megastructures like a hydroshell, which allows truly huge aquatic environments, dwarfing planets but avoiding crushing water pressures. We will be looking at this in terms of a few options for gravity: microgravity, gravity simulated by rotation, natural gravity, and artificial gravity. We will be looking at scales from small habitats up to planet-sized ones, and even ones dwarfing planets in scope. We will also be looking at purposes, whether it's a civilization that's aquatic in nature or it's more of a preserve, such as if we built large marine habitats as nature preserves rather than for us to live in, or for highly uplifted dolphins or whales to live in. We will also play with some interesting features you might have in these, like vertical reefs or submarine islands inside and under the water. Now, to begin our discussion, there's two critical concepts we need to understand. First, that water under gravity will grow in pressure as you go down, each layer above pressing down on you more. And second, that gravity can be mimicked by rotation and centrifugal force, and water will still grow in pressure under that pseudo-gravity. This is going to cause us some problems that, as we will see today, make it tempting to either minimize gravity if you can, or opt for small rotating habitats, or rather, skinny ones. Spin gravity habitats, the most popular example of which is the O'Neill cylinder, rely on the core assumption of Einstein's general relativity, which is that gravity and acceleration are essentially interchangeable under the equivalence principle. What this means is that objects which are spinning around in a circle while maintaining the same speed are constantly undergoing a change in actual velocity, the direction changes, and this is acceleration, and this makes that spinning, accelerating object effectively under gravity. A man in zero gravity, but being spun on a rope like a sling, whirling around in a circle, is going to feel as though they are under gravity, pulling them outward away from the center of that spin. This is centrifugal force, and is what makes water and clothes press the side of a washing machine in the spin cycle, or makes you tilt when your car goes around a corner or bend. Now, centrifugal force is often called a fictional force or pseudo-force, and that makes folks think it does not exist. Amusingly, modern physics often regards gravity itself as a fictional or pseudo-force as well, but critically, it just refers to how the source of the force is your acceleration, rather than the gravitational pull of mass or electric charge or such. Without dipping into frames of reference, inertial and non-inertial, the key notion is that if you are inside a big spinning cylinder, drum, donut, or so on, you will feel pressed down to the surface the same as you would on Earth. Folks sometimes misunderstand this and think if they jumped up, they would float, but quite to the contrary, you'd fall right back down again. Folks ask if this can work as real gravity, and the answer is yes. Just ask the clothes in your washing machine, or the astronauts in the space station. They are still entirely inside Earth's gravitational field. It is a bit weaker that high up, a few percent, but that's barely noticeable. They float around because that station is whirling around Earth, and the centrifugal force is negating Earth's gravity on them. This is one way of understanding how orbits work, and why speeds needed to orbit decrease the further away you go, as gravity drops and as acceleration needed to turn at such a radius increases. For a lot of channel regulars, that was old hat, but I felt it needed repeating since we haven't covered it in a while, and not everyone on this show is a long-time listener. Also, we need to understand that whirling an object around to create this pseudogravity puts it under tension. Whirling a stone around on a rope makes that rope taut, and if you spin it fast enough, or use too big a rock, the tension will rise too high and will break that rope. How strong a material is in this way is called its tensile strength. Normal gravity can break stuff too, under sheer weight of stuff piling on it, compressing it, and this is called compressive strength. Materials have tensile strengths and compressive strengths, and the two have little relation. A given material can be very strong in one of those strengths but weak in the other. How fast you spin a cylinder, combined with its radius or diameter, will control how strong gravity is at the surface. It is linear too, so halfway between the center and the edge, it's half strength, and zero at the center. This tension on the material the cylinder is made out of is essentially identical to what a suspension bridge here on Earth experiences, and a bridge a kilometer long would need the same strength as a cylinder habitat a kilometer in circumference, or 0.16 kilometers in radius, or 520 feet in radius. Steel can handle such a length or circumference or radius, but it is quite a burden on it, and only made worse by adding materials, such as lots of cars and trucks driving on that bridge, or all the concrete or asphalt making the road on it. Same for cylinder habitats, all that dirt and water inside them add up, and a few meters of dirt is pretty heavy, several tons per square meter, so we tend to think that any hills inside such habitats would be hollow, filled with tough but ultralight fillers like aerogel that could be covered with a thin layer of dirt, or by putting dimples and rises in the hull itself. This mostly works because land-based life is really pretty two-dimensional. We have plenty of hills and valleys, but it's the surface we live on, and a house at the top of a hill and one down a valley still have a basement and second floor just a few meters above or below that surface. Marine life is a bit trickier. Our oceans here on Earth average about 3,000 meters in depth, and each meter of depth represents another ton per square meter of stress. So whereas a thin coat of dirt a few meters or 10 feet deep might put 10 tons of pressure per square meter down on your drum hole, a few kilometers of water would put down 3,000 tons per square meter. That means your hull needs to be 300 times stronger to handle such depths of water inside. Now there's a couple caveats here, and the first is that, as I mentioned, gravity experienced inside a rotating habitat is linear to how far from the center you are. So the upper layers of water inside such a habitat push down less because gravity is weaker up there, though only if that habitat's radius is fairly similar to the water depth. If the habitat is 1,000 kilometers in radius, then even if your ocean is 10 kilometers deep, the top is only experiencing 1% less gravity than the bottom, and it's fairly trivial, much as the change in gravity on Earth from altitude or depth is when we're only talking about mountain peaks or ocean trenches. But what it means is that a cylinder full of water a kilometer in radius is only getting about half the stress on that bottom as that depth implies from the weaker gravity, 500 tons per square meter rather than 1,000. Also, it means that you have a 2 kilometer wide stretch of ocean there, since it's water all the way through and its diameter is 2 kilometers. Though you might want a layer of air in there. And we probably want to ask why we need that much depth. There are creatures living in the deepest part of our oceans, fully 11 kilometers deep in the Mariana Trench, and we may want to simulate that environment or even higher pressure ones. However, the overwhelming majority of ocean life lives in the epipelagic zone, the thin skin 200 meters deep where sunlight can still meaningfully penetrate water and fuel photosynthesis. On our planet, that epipelagic zone also fuels what life is below it, as things either swim up there for food, hunt things swimming down from there for food, or wait for dead matter and detritus to come falling down, what we call marine snow. Now, there are geothermal vents and such fueling some life too. Indeed, the principal current theory on the origin of life puts those vents as the best candidates for life to have emerged at, and been sustained by until photosynthesis evolved a billion years later. We can replicate such thermal vents on a space habitat, of course, and one of the cool things about artificial worlds is all the flexibility you get. They are the difference between living in a natural cave and a well-built mansion. If you want a habitat dense in life but only running on geothermal vents, you can do that, and create worlds worth of ecosystems for all those life forms confined to those tiny undersea oases of heat and life. That might be some interesting engineering too. You might have a nuclear reactor's secondary cooling circuit venting directly into the hab. Water coming from vents needs to be highly mineralized, so you would either need a tank of dissolved minerals to inject into the stream of hot water, or solid mineral blocks that are dissolved by the hot water. Either way, your engineering would need to avoid minerals precipitating onto critical components like turbines or nozzles. Key thing about megastructures, they do need maintenance. You might instead opt for something like a passive decay radioisotope supply, or even the natural fission reactors that sometimes formed in Earth's deep past around uranium-rich pockets. With artificial habitats, we so often focus on using the sun or mimicking it that it's easy to forget that we have some other options for life. Nonetheless, virtually all the life in all seas lives in that sunlit epipelagic region or close to it, so we could build a skinny habitat just 100 meters in radius, reflect and pump sunlight into it, and actually get some fairly interesting currents and motion going from all that spin and varying gravity by depth. The smaller a habitat is and the faster it rotates, the more pronounced the effect of gravity varying by height, and also the Coriolis force, which is another fictitious or inertial force like centrifugal force related to spin, and one strong enough that it's a big player in all weather in spite of Earth being wide and slow spinning. We will be talking about suspending islands or reefs in bigger water habitats later today, and these weird currents are one option for doing that, as rocks should fall down, but much as gliders can remain hanging in the air by using rising currents of moving air, you could get some metastable pockets of ocean on your habitat where coral reefs glide or hover on currents of moving water. You also have the ability to hang your islands by a tether from the center, which is exactly as sturdy as the hull since it uses the same principle of tensile strength, much as islands and continents use compressive strength here on Earth. The cool difference is that tensile strength is generally flexible, so a big rock floating in the middle of a marine hab held by a tether to the center could also move around and twist like a pendulum. So imagine a big three-dimensional ocean with submarine islands moving around, underwater, on their own orbits and paths, circularly, elliptically, and potentially all sorts of zigzags, especially since one cool thing about a tether is that you can winch it up or down too, and run power down it, for engines or turbines or air compressors. Part of the reason our oceans are so dead on a volume-by-volume basis with land is that in spite of being huge in resources and sunlight, those two are not in the same place much. With the exception of a narrow band along the coast, most of the nutrients in the ocean sit on the seafloor in darkness, whereas most of the sunlit part of the ocean is starved for nutrients. An engineered ocean habitat is capable of using water currents and lighting to bring nutrients and light wherever they are desired, extending epipelagic zones indefinitely. We often discuss doing this for Earth's oceans or subsurface oceans like we expect to find on icy moons, like Europa or Callisto, and I call them vertical reefs, as one would expect these chains of light to result in fairly parallel roars to what normal reefs do, creating dense local pockets or ribbons of ecology and biomass. Indeed, we tend to assume lighting on rotating habitats will be artificially generated to begin with for mini-hab designs, generated by electricity or moved in by mirrors or fiber optic cables, and I would say this would be a common approach except for one big factor: hull stress. We don't really want to involve deeper layers of the sea except where it's either needed for the ecosystem to function, or because that is the ecosystem we are making because it's supposed to be simulating the Mariana Trench, not Caribbean archipelagos. If we want to make strictly epipelagic lit regions, only more of it, we opt to make our habitat longer, not wider or deeper. Once you get to that peak radius and depth for your sea based on your needs and material constraints, you don't build any wider, you just build longer. Your cylinder becomes more of a skinny pencil or needle shape, or even a very long sausage-like linked arrangement of many chained together, or a rope like a mega-long hab, what we call a topopolis, which might be millions or even billions of kilometers long, but only a few kilometers wide. Such long habs or sausage-link affairs are good ways to place similar but distinct ecosystems nearby in a way that allows only the amount of interchange that you want between them, as a means of controlling invasive species or encouraging migration. So what if we want really deep oceans but don't have the materials for it? Nothing strong enough or cheap enough? One thing to remember is that a lot of the ocean's dependence on gravity is just to keep things moving from above to below, and we are quite capable of pumping nutrients and air bubbles around inside a microgravity environment too. But as I mentioned, we think a lot of icy moons might have subsurface oceans, and they are considered strong candidates for extraterrestrial life, albeit probably low in biomass and biodiversity from the lack of sunlight. we tend to assume the lower gravity is not an issue there, where it's often weaker than our own moon, and there are good odds Earth-based marine life would require little adaptation to lower gravity, say a tenth of Earth normal, and that right there lets you seriously increase your depth of sea and radius of habitat, because it's still enough for there to be a real and meaningful concept of up and down, but each layer of water presses down less. This potentially allows much deeper layers of ecology in your habitat, as pressure will shift more slowly with height. It is too soon to tell if low gravity is viable for terrestrial marine life. Zero gravity seems to have been rough on fish we tested thus far, and even if low gravity is, it might be viable but require lots of adaptation, natural or genetically engineered, which somewhat defeats the point of building a nature preserve. We will have to see on those, and it might turn out we need full gravity, in which case we might need to be considering using rare oceanic planets of the right gravity as those preserves, or very long thin water habitats. One other option though might be a shell world. Now normally we contemplate this as a hollow metal shell with dirt and water on top of it, with either a black hole or compressed hydrogen or helium inside, serving as an abundant and cheap source of natural gravity. However, a hollow sphere itself generates gravity with the normal properties by and large. The difference is that all your gravity is generated by that shell, and its higher layers exert no gravity on its lower layers, so that counterintuitively, the gravity decreases as you go down the layers. It still pulls inward though, it's not reverse gravity. This has some interesting options for habitats because a sturdy hollow metal shell with some rock over it, nothing under it, and many kilometers of water above might make for a huge and viable ecosystem dwarfing anything Earth could have. In our discussion of super-Earths last week, I mentioned that since Earth is 5.5 times denser than water, a planet with the same surface gravity as Earth, but composed entirely of water, would be 5.5 times wider than Earth, with over 30 times the surface area and obviously much deeper seas. But if those seas weren't very deep at all and just ended with a rocky shore and hull 10 kilometers below, things shift quite a lot. Incidentally, if this shell world and how it's not collapsing downward is a new concept to you, see our Mega Earths episode for a discussion of the mechanics and technologies required. Otherwise, just assume it's magically strong material for now. Water is ridiculously common in this universe, albeit mostly as ice, and coming up with entire planetary masses of it is much easier than coming up with rock or steel or even air. A spherical shell 10 kilometers thick of Earth's mass in water and some rock and hull would have a volume of 6 trillion cubic kilometers and a surface area of 600 billion square kilometers, about 1,200 times that of Earth's surface, and a radius of 2,220 kilometers, 34 times that of Earth, and over half the distance out to the moon, closer to the size of a star than a planet. However, because it only has Earth's mass, the surface gravity would be 34 squared or 1,200 times weaker, amusingly meaning the pressure even 10 kilometers deep would still be less than 1 atmosphere, Earth normal pressure, before even accounting for the drop in gravity as you went down, which for these shells much thinner in thickness than in radius would be linear to how deep you were. Now, critically, if you double the structure's radius but keep the same thickness of sea, 10 kilometers, that surface gravity will stay the same because you quadruple the surface area and thus quadruple the mass, resulting in same strength of gravity no matter how big you go, and you can push this up to Birch planet scales. Galaxy mass artificial planets, again see the Mega Earths episode. However, if we increase thickness a bit, say to 1,200 kilometers deep, then we've got 120 times the mass or density on these objects, for a surface gravity a tenth of what Earth has, meaning pressure is only rising at a tenth the rate and will actually rise slower as you get deeper, and those higher levels of water cease contributing to the gravity pulling down. Any spherical shell of mass generates no gravity inside it, be it one step inside or at its center, so way down at the bottom, 1,200 kilometers deep, over 100 times the depth of the Mariana Trench, our pressure is only a 20th of what we would expect, albeit 5 times higher than at the bottom of that trench. One where the water was only 120 kilometers deep, giving only 1% of Earth normal gravity at the top, would be one where you could swim around with normal scuba gear all the way to the bottom. This also means biological life can run that whole range, especially with supplemental lighting such as vertical reefs, And with heaters and pumps and mixers down on that shell, you could simulate thermal vents too, and massively more densely. So you could get some huge depths of ocean habitable to life, and densely so. Oxygen is incredibly common and hydrogen vastly more common than that, but even without putting much effort into cramming them together, we get estimates as high as a dozen times Earth's mass in water in our Oort cloud alone, which for the 120 kilometer deep shell example would result in a shell as big as our first thin version, 1200 times Earth's surface area, all of it composed of a massive sea of low pressure. I am going to define worlds or megastructures of this type as a hydroshell world or just hydroshell, one where the water pressure doesn't rise beyond anything we find on Earth, indeed may stay well short of it, but which is huge compared to Earth, and we will just prefix kilo, mega, giga, etc. under hydroshell for its total mass relative to Earth. This is, to the best of my knowledge, a totally new type of megastructure that came to my mind while writing the script with the power flickering here at home from 40-mile-an-hour winds and plenty of rain, so I doubt I've done more than scratch the surface of what these surface shells of sea might offer for combinations, and I'd encourage all mini math and world-building savvy folks to play with the options on the idea and let me know what you come up with for options and limits. Same for our Topopolis sea worlds. One that comes to mind is neutrally buoyant submarine habitats with air-filled domes that are pressurized to right around the 1 atmosphere mark, since the dome would have no real stress on either side of it, making air bubble submarine island habs a real and decently safe option. And you could play with partial pressure and air mix to let your islands be at various depths. These could get big too, continent-sized, complete with kilometers of vertical change in terms of mountains and valleys on them. They could also be very three-dimensional rather than just that classical image of a thin island with a big dome over it. You probably do lots of bubble domes instead of one big one, and you probably have lots of gas packed in your rock layer like aerogel below the ground to help with buoyancy, but this offers some huge options for habitable land on such worlds, which again can be hundreds or even millions of times Earth's surface area. Any rock in your hab that is exposed to water would become coral reefs, which would be just delightful. Of course, you have the option to genetically engineer gills into folks for your mermen and mermaids, but I suspect a nice safe dome operating well under known cracking pressure would be preferable for most potential colonists. This would work on subsurface oceans of icy moons too, as they have low gravity and a similar slow rising pressure scale. We also have the option of an oceanic hoop world, though we'll save discussions of that for another time if we ever remake our old hoop worlds episode. Needless to say, if you can create gravity artificially like we see so often in science fiction, or have anti-gravity, you have some additional options for big water worlds. Now it also might turn out that gravity is not needed for marine life, or you might choose to genetically engineer all your marine life to no longer need gravity, which sure makes building such habs easier, though so long as little gravity is needed it shouldn't pose too rough an engineering hurdle, as we've seen. And if we are actively pumping air bubbles and nutrients around our habitat anyway, then we need not rely on gravity alone for that sort of effect. The problem is at a certain point, you do get gravity if the habitat is big enough, but we are talking hundreds of kilometers wide before it even got to 1% of Earth gravity, so you can make some very big marine habitats in microgravity, but as they get bigger, they get more gravity. One option though would be something that is mostly water in the large moon range of mass, and which had an artificial sun at its center. Such a water globe might have an atmosphere outside, or a layer of ice as its skin, or a metal hull, depending on size and engineering concerns and preferences. This central sun need not be sun hot, it could simply be light generated by LED, but it is worth noting that at a certain sweet spot of temperature and gravity, water falling down on a white-hot pseudosun is going to evaporate faster than it can fall and shove water back up too. This should seem to create some sort of brilliantly bright, bubbling eternal storm at the center, which would be quite a cool effect, I'd think. However, I could definitely see a lot of those sorts of artificial stars, scaled down to something more like a big power plant, floating around these sorts of world seas. You might intentionally power them up too strong for anything to live right next to them, producing that bright and hot boiling effect, just to ensure they didn't get covered in life forms and algae blocking their light. You might extend long metal or ceramic tentacles or spurs off them for life to grab hold of or let them migrate untouchably with things needing to swim along. Boiling and seething and bubbling around your world sea, these sea suns might just have bubbles of ecology roaming around with them if you left them to wander. Now, as we discussed last time in Super-Earths, between those and subsurface oceans of various icy moons and planets, we are not expecting to have any sort of shortage of natural oceans to use or terraform, and they should generally be easier to terraform than planet surfaces and atmospheres by and large. Additionally, I would expect most of humanity will want to build its habitats with lots of land and shallower seas and lakes, lots of beaches and reefs and sea bottoms you could scuba dive down to, though this assumes we have started building lots of megastructures before engaging in a lot of genetic tinkering and other transhuman paths, and that's a very debatable thing. So when it comes to megastructural habitat preferences, we will leave it at assuming tastes will vary. However, the purpose of megastructural habitats is to let you build far more worlds with far more living area than natural planets would ever supply, tailored to your wants and desires, so it lets you get away with using only a tiny fraction of your worlds for those which wouldn't be human paradise habitats, and still have billions of times Earth's living area devoted to weird worlds and habitats and nature preserves and more. Untold trillions of ocean habitats, big and small, Earth-like and unearthly, normal and alien. And as we saw today, we have no shortage of options for building space habitats with deep blue seas. So today's episode was all about water, and it has some pretty interesting facets we had to gloss over a bit. For instance, those entirely water-based worlds we mentioned this week and last week obviously cannot form naturally, but they can't be made above a certain mass without the material undergoing a phase shift into exotic ices of various types and densities, so that if they were deep enough they'd have layers and cores of those exotic ice types, throwing off our calculations a bit. And indeed, that's one of the advantages of the various megastructural marine habitats we discussed today, like the hydroshell, or simply skinny rotating habitats. Of course, there's even more strange effects on systems from adding things like salt to water, a critical factor in our own oceans, and with some very surprising effects. There's an excellent interactive examining how salinity affects water temperature and behavior in Brilliant's scientific thinking course that helps demonstrate this, and it's just one of the course's many interactive exercises that let you experience the principles of science firsthand. Brilliant is an online interactive STEM learning platform that helps you gain a deeper understanding of concepts in math, science, and computer science by taking you through the subjects piece by piece in visually stimulating, hands-on ways. Brilliant is also constantly expanding their catalog of courses, so whether you're a beginner, an expert, or anywhere in between, there's an interactive lesson to help you improve and learn, and this hands-on, interactive approach to learning is the hands-down best way to learn. To get started for free, visit brilliant.org/IsaacArthur or click the link in the description, and the first 200 people will get 20% off Brilliant's annual premium subscription. So that will wrap us up for today, but don't forget to join us this Sunday, February 27th at 4 p.m. Eastern Time for our monthly livestream Q&A, where we take questions from the livestream chat and answer them live. Speaking of live, I haven't actually done a live and in-person talk since COVID-19 hit us, and that's finally thawing out, so I have the first of a few spring ones coming up in early March, when I'll be giving closing remarks for the conference on the future of space cooperation between the US and Japan on March 7th and 8th, hosted by the RAND Corporation. And there's going to be some great speakers there, starting with David Kipping from Cool Worlds and Pete Warden, the director of the Breakthrough Starshot Initiative. I'll attach a link for the event and registration to see it in person or online in the episode description. Before that, we have our first episode for March, and we'll be looking at how civilizations might mass manufacture many of the heavier elements their engineers might need for building megastructures in our episode, Nuclear Transmutation. Of course, such megastructures often assume lifespans similar to the planets they emulate, so on March 10th we will take a look at how you could build a machine designed to last 1,000,000 years. Then we'll have our March Sci-Fi Sunday episode to look at the concept of synthetic life. And we will keep to the sci-fi theme as we return to our Alien Civilization series to contemplate the concept of clandestine extraterrestrial operations and covert aliens. Now, if you want alerts when those and other episodes come out, make sure to subscribe to the channel and hit the notifications bell. And if you enjoyed this episode, please hit the like button and share it with others, and leave a comment below. You can also join the conversation on any of our social media forums, find our audio-only versions of the show, or donate to support future episodes, and all those options and more are listed in links in the episode description. Until next time, thanks for watching and have a great week.